Hello everyone. The title of this video is Factoring the Greatest Common Factor, or GCF, of a polynomial. Now, everything I'm doing in this video, every exercise, every example, is taken directly from a free online textbook at openstacks.org, and it's their algebra and trigonometry text. I'm also in section 1.5 titled Factoring Polynomials, and all I would ask that you do is go to this text and read through the factoring the greatest common factor of a polynomial part of the section. And the examples I'm doing in the video are taken from the examples and try-its in this section, and also from some of the even numbered exercises at the end of the section related to this objective. I will have timestamps for each example I do in the description of the video below. Alright, so you should be able to navigate the video more easily. If you want to go from one problem, one example to the next more quickly, click on those timestamps. I also request that when I start a new question in the video, pause it and try to work it out yourself first before watching me do it. Because if you're just watching me do these things and not practicing yourself, chances are you're not going to learn all that much. Alright, so I've written out my examples on paper. And again, it's factoring the greatest common factor, GCF, of a polynomial. And we have the same instructions for each of these exercises. We're asked to factor by pulling out the GCF, or greatest common factor. Alright, so I'm going to, off to the side here, talk about how we're going to find the greatest common factor, right, the GCF, of a polynomial. So the first thing is to factor each term completely. Right, I'm going to list the factors of each term. Now remember, factor means write as a product, right? Write as a multiplication problem, right? A multiplicative expression, however you want to say that. I'm going to factor each term completely. Now a term of an expression is a product, and these are products that are separated by plus signs, separated by addition. So in this example here, example 1, I have x times b squared minus a. This is a product. And then you have a plus sign. Right? So this is a term of the expression. And then plus, and then we have, another product here, 6 times the quantity b squared minus a. Right? This is another term. Right? So let's do that here. So the first term is x times b squared minus a, right? And this has two factors, a factor of x and a factor of b squared minus a. Remember, if something is in parentheses or brackets, it's considered, a single number, right? A single factor. And 6 times this b squared minus a, this factors to 2 times 3, right? 6 breaks down further to 2 times 3 times, and then, this quantity b squared minus a, I promise you, doesn't factor any further. You cannot break this apart into a product of other factors. Alright, then after factoring each term completely, which we have done here, the greatest common factor, right, the greatest common factor is made up of the factors that every term shares. Is made up of is the product of the factors that every term shares, or every term has in common, right? That's the word common in greatest common factor. All right, so if I look at these two terms, right, these two terms and their factorizations, they share this factor of b squared minus a, and that's it. Those are the only factors that is shared by, that's the only factor that is shared by these two terms. So in this particular example, the greatest common factor, the GCF, is just this quantity b squared minus a times, nothing else. Right? They share nothing else. All right, and then finally, now that we're asked to factor by pulling out the GCF. After you find the GCF, you use the distributive property, or I'll say reverse the distributive property. Because really, no matter which way you're going, you're using what's called the distributive property, but most people know it in the one direction. Right? Reverse the distributive property. So that's where if you have some expression a times b plus or minus, and then that same expression a, that same factor a times c, they have a common factor of a. You pull that out, right? Pull out the factor, and then that'd be multiplied by a quantity of what's left over. When I remove a, would be b plus c. Right? So that's why I call it reversing the distributive property, because technically both directions are the distributive property. It's just most people, when they think of the distributive property, think of putting this a over the quantity b plus c. All right. So our original expression, x times the quantity b squared minus a plus 6 times the quantity b squared minus a, the only thing they have in common is this, right? The greatest common factor. Right? The only thing both terms have in common is this quantity b squared minus a. So I pull that out. Right? So I write the greatest common factor first. Right? So there's the GCF as its own factor, multiplied by, and then another quantity. And again, I'm just reversing the distributive property here. Just what would be left over in each term if I remove b squared minus a? And that would be x in the first term plus, and then if I remove b squared minus a, you'd have 6 in the second term. All right, and this is the remaining, what's remaining. Remaining factors in each term after removing the greatest common factor. And there we go. And that is this expression factored. I'll put it in a box. This is the end. Right. And again, when they say factor, right, you want to write the expression as a product. This is a product of two factors. You have your GCF as one factor times this quantity x plus 6 as the other factor. Right. Now to check, to check your results, to check factoring, you just multiply, right? So to check factoring, to see if you factored correctly, you multiply and see if you get, the same expression that you got in the beginning. Well, here was my final result, right? B squared minus A, that quantity, the GCF, times the quantity x plus 6. And what I'm going to do is, distribute. Earlier I reversed distribution. Now I'm going to distribute. I'm going to take this b squared minus a and distribute to this x plus 6. And this would be equal to x times the quantity b squared minus a. And notice that I'm putting them in the, it doesn't matter what order these come in, because multiplication is commutative in the real numbers, right? All these variables and whatnot represent real numbers, and it doesn't matter what order you multiply real numbers in, you get the same result. So bear with me here if I'm changing order. Then we have plus, and then 6 times this quantity b squared minus a, and look, this is the original expression that we were given. So great, that means our factorization is correct, right? If you multiply what you factored and you get the original expression back, then that means your factoring was good. You did a good job. All right, now here's a little more involved way of checking. This is more testing than actually checking. I guess there's not that much of a difference. But you could test with some technology. All right. So what I have, what I'm going to show you online is there's this free online graphing calculator called at desmos.com, desmos.com. And another way to test if your factored expression, is actually equal to the original expression. Two expressions are only equal when they have the same value, no matter what you plug the variables in, what you plug in for the variables. So this expression I started with and this factored version of that same expression, they should take on the same value no matter what I plug in for x, a, or b, right? And you could test it out by hand. You don't need a calculator for this, but I'm going to use one. Replace a and b and x with some numbers in both of these, and you'll see you end up getting the same result every single time, right, which I'm going to show you here. Right? So the nice thing about this is you can enter multiple variable expressions in this Desmos. I have x times the quantity b squared minus a, and you see it's going to say add sliders for a and b. I'll just do that. And now that now the value of b is 1, the value of a is 1. Okay. And then plus 6 times that same quantity, b squared minus a. Right. And yeah, and we can change the value of b to anything we want, change the value of a to anything we want. And what I'm going to do is I'm going to bring up a table for this expression where different values of x are plugged in, and then you get different values of y, and you can change the values of x here. And again, the value of b and the value of a are down here, right? And you can change them if you wish. All right, so that was for x times b squared minus a plus 6 times b squared minus a. I'm going to do the same thing for the other expression. Take b squared minus a times the quantity x plus 6, right? This was our factored version. Let me move this up next to the other one, right? And you see that they're the same thing, actually. Let me change. Actually, I can go in and change the color of this. and you'll see that their graphs, the graphs of these expressions are the same. See, there's red, then there's purple right on top of red. All right, when I turn it on, turn it off, turn it on, you can see hopefully on the graph there, this line. Yeah. Now if I make a table for it, we'll see the same values appearing. Right? Make a table, and you see when x is -2 and b is -1.7 and a is 0, they have the same values all the time, right? 11.56 when x is -2 and 14.45 when x is -1, 17.34 when they have the same values all the time. And if again, we can change b and a to anything we want. Change b to 5.1, say a to -0.42, and again the tables are the same for the same values of x. Right. So that's a way you can test. I mean, just because these 5 values work doesn't mean it's always true, but you get a good feel for the fact that, hey, these expressions are probably the same. Right? So I'm going to clear all this out now. But yeah, so that's a way you can test, if two expressions are the same, right? Test to see if they actually take on the same value, no matter what the variables are replaced with. All right. So I'm going to follow these same steps. We're going to factor each term. First, I have to identify the terms, and again, they're just products separated by addition, separated by plus signs or minus signs, but you'll see that minus signs are part of the next term. Then the greatest common factor will be the product of the factors that every term shares. And we'll talk a little bit more about the construction of the greatest common factor throughout the video as well. And then finally, pull the greatest common factor out. And then the other factor will just be made up of the factors remaining in each term after the greatest common factor is removed. Wonderful. So next question, same instructions. Same instructions. 14x is a term. So I'm going to list the terms here. 14 times x, that's a product before a plus sign, before addition. So there's a term. Then 4 times x times y, that's the next term. And then, remember this minus 18xy squared can be written this way. This is 14x plus 4xy. And then remember, when there's subtraction, that's just addition. You can write it as plus -18xy squared. Right, like that. But usually people don't write things like that with the plus a negative. But this -18xy squared is the last term of this 3-term polynomial, or a trinomial. Alright, then we'll do their factorizations. Right? So 14x, when I factor it completely, 14 breaks down to 2 times 7, and then x is just x. So there's 3 factors, 2 and 7 and x. 4xy is 2 times 2, right, breaking down 4 completely, times x times y. Right, and those are just x and y. And then negative, they'll be negative, right? Just put a minus sign here. Then we're breaking down 18x and y squared. 18 is 2 times 3 times 3, right? 2 times 9. And then x to the first is just x. And then y squared is 2 factors of y. Remember, that's what it means for y squared. So I factor every term completely. And then we look for the factors that they share, all terms share. And we'll start making the greatest common factor, the GCF, from this. So I noticed that there's a factor of 2 in all 3 of them. So that's going to go in the GCF. So I'll write that down. 2 times. There's no factor of 7 in these 2, so 7's not common to all 3. There is a factor of x in all 3 of them. Alright, so that's going to be in the GCF. 2 times x, or just 2x. And that's it. Those are the only factors that are shared by all the terms. All right, so the greatest common factor, this isn't the answer, but it's going to help me get to the answer, right, is 2x, 2 times x. So, bringing this down here, this will factor in the following way. So I pull out the greatest common factor, right, 2 times x. Again, the first thing I do is I'm just reversing the distributive property, right? So the greatest common factor is its own factor multiplied by another quantity. And in this other quantity, this other factor, I just put the factors that remain in each of the terms when I remove the greatest common factor, and that's what's nice about having these factorizations listed off. If I remove 2x from the 14x, you're left with 7. Plus, right, if I remove the 2x from the 4xy, you have 2y left over. And then minus, right, then the last term has a minus. And then if I remove the 2x, the GCF from the last term, you have 3 times 3 times y, or 9y squared, when you multiply those out. And there we go. Right? It's the greatest common factor multiplied by the quantity of, the factors that remain in each term after I pull out the greatest common factor. And this is our final answer. And again, please check your result. Always check your work. Always. So if I were to take what I have there, 2x times the quantity 7 plus 2y minus 9y squared, and I were to multiply them by distributing the 2x, 2x times 7 is 14x, 2x times 2y is positive 4xy for the next term, 2x times negative 9y squared is negative 18xy squared, and we get the original expression. Hooray. So it works. And again, we could, if we wanted to, I can go to the Desmos site here. All right, we have 14x plus 4xy minus 18xy squared. All right. And I think we can, I think the confusion here is with y. So you know what I'm going to do? I'm going to replace y with another letter, a. Right? So that way we can just, you should be only, the graph, it'll only graph functions of a single variable. So if you have multiple variables like x and y, it's going to confuse y for the usual y. So I'm changing it to a and adding a slider in there. Now it's graphing stuff, right? So see that purple graph showing up here. All right, and then so I'm just replacing y with a. Then our other, we factor out 2x times, and then 7 plus 2y, but I'm calling that 2a this time, minus 9y squared, but that's a squared. Right, you see it's the same exact graph. They're right on top of each other. Meaning if you were to look at a table, and even if you change the values of a, right, they're the same graph every time, right? That means they have the same value. And if you were to look at tables, you'd see they have the same value for the same values of x, right? They're both, let me move this one up. Get the tables close to each other. All right, and you see when x is negative 2 and a is 0.8, and x is negative 1, 0, 1, 2. See, they got the same exact tables, the same exact outputs. And you can plug in whatever you want for x, and you'll see the same exact outputs, right? If I plugged in 5 for x, I get 28.4 for that expression. Plug in 5 for x down here, 28.4, right? They have the same value all the time. So let me clear this out and go back to the paper. Great. All right, next one. Same stuff. All right. And this time I'll show you a bit of a shortcut for the greatest common factor. So we have 30x cubed y, that's one term. All right, so again, I'm going to list the terms. We have, this is a product, 30 times x cubed times y. That's a term, 30x cubed y. The next term is, plus, minus, is negative 45x squared y squared, right, another product, plus, and then another term, 135 xy cubed. All right, then over here there are factorizations, right, when you factor the terms completely. All right, so 30 is 6 times 5, 2 times 3 times 5. Right, so this is 2 times 3 times 5. And then x cubed is x times x times x. And y is just y. Right, there's the complete factorization of the first term. All right, the next term has a negative, right? Don't worry about that so much. And then 45 is 5 times 9, which is 3 times 3 times 5. X squared is x times x. Y squared is y times y. And then 135. 135 is a multiple of 5, right? That's 5 times 27. And 27 is 3 cubed. 3 times 3 times 3, that's 27 times 5, which would be 135. And then times x. And then y cubed is y times y times y. All right. And then from this, we can easily state the greatest common factor. So, this has a factor of 2, this term, but these don't. They all have a factor of 3. Right? Every single one of these terms shares a factor of 3. So 3 is going to be a factor in the greatest common factor. So 3 times. Then they all have a 5 as well. They all share a factor of 5. So we have 3 times 5, or 15. Right? They all share a factor of x. Right? Every single one of these terms has a factor of x. So times x in the greatest common factor. No more. These two have x again, but this one doesn't have another x. They all share a factor of y as well. Y to the y. And there we go. And that's it, right? These two have a y, another y, but the first one doesn't. So those are the only factors that all three terms share. So the greatest common factor when simplified is 15xy. Right. Now, that's not the answer. Now, a little shortcut for you. All right, just a little shortcut for you. If I was to write these out with powers, we have 2 times 3 times 5 times x cubed times y to the first, right, if you want to put the power on that. That was for the first term. Then the second term was negative, and then 3 times 3 is 3 squared, and times 5 to the first. Then you have times x squared times y squared. And then the third one is 3 cubed times 5 times x times y cubed, x to the first times y cubed. And I guess you can put the first power on everything without a power, right, if you want. And then for the greatest common factor, so you could also do this. Look at the things they share. Well, they don't share 2's, but they do all have 3's. So it's 3 raised to a power. And then this power is the smallest exponent on the 3. The smallest exponent. So what's the smallest exponent on 3? Right, that would be 3 to the first. That is the smallest exponent on all these 3's. And then I notice, again, they all share a 5. Right? So all of them have a 5. So there's going to be 5 to some power. And again, that's going to be the smallest exponent on the 5. Well, the smallest exponent on the 5's is obviously 5 to the first. They all have 5 to the first. And then they all have x. So the greatest common factor is going to have x to some power. And it's x to the smallest exponent on x. The smallest exponent on x is x to the first. And then they all have y to a power, so the greatest common factor is going to have y to a power. And once again, this is going to be the smallest exponent on y. And the smallest exponent on any of these y's is again y to the first. You got y squared, y cubed. And we get the same exact thing. Right? 3 to the first times 5 to the first times x times y, that's 15xy. Alright, so that's another way that I'm going to be doing it from here on out. Instead of listing all individual factors like I did previously, I'm going to write the factorizations with, as primes to powers, right, with their exponents. And then we're going to look at, well, what primes, what bases do all the terms share? That'll be in the greatest common factor, and then the power on that will be the smallest power that shows up. All right. Okay, and then we get to the factorization now, right? So the 15xy becomes its own factor, right? I pull out the greatest common factor. And then what would be left over when I remove those? Now, this is a nice way to see what's left over. Now, if you want to keep listing the individual factors and see what's left over when I remove the stuff in the boxes, right? Remove the greatest common factor of 15xy. First term, you'd have 2x squared plus, minus, minus. And then the next term, what's left over after removing the GCF is 3xy. And then plus, and then the last term, what's left over when I remove the GCF is 9y squared, 3 times 3 times y times y. And there we go. This is the factored form, right, when I factor out the GCF of the original. And again, now this time I'm going to leave it to you, but don't forget to check your work. Actually multiply, distribute the 15xy, and see if you get 30x cubed y minus 45x squared y squared plus 135xy cubed. See if you get that back, and you should, if you did things correctly. Right. Or you could check with, do some testing with some technology, like that Desmos website. All right, and I got just one more of these. So again, we got another 3-term. Now, not every polynomial has 3 terms, right? You saw the first example just had 2 terms. So I'm going to do the same thing as previous examples. Let's list the terms. Right, and I'll do it the long way and the quick way, finding the GCF. And then in future videos, if I'm ever needing to find the GCF, I will obviously do it the quicker way. Alright, so the terms of this polynomial, this expression are, the first product here, 36 j to the 4th times k to the 2nd. And then the next term is negative 18 j cubed times k cubed. And the final term right after this plus sign is this product, 54 times j squared times k to the 4th. Alright, and then we'll do their factorizations. List out all the factors, all the prime factors of each of these terms. Now 36 is 2 times 18, which is 2 times 9. 3 times 3 is 9. So this is 2 times 2 times 3 times 3. Right? That's 36. Broken down to a product of primes. J to the fourth would be, j times j times j times j, right? There's j to the fourth times k squared, so times k times k. Or, to do the shortcut way, do 2 squared times 3 squared times j to the fourth times k squared. Right? Both of those are fine. You've broken it down to a product of primes or powers of primes, and we're going to just treat the variables like primes. And then we have negative, and then 18 is 2 times 9, 2 times 3 times 3. J to the third, j times j times j. K to the third times k times k times k. Or with powers, this would be negative, and then you have 2 to the first times 3 to the second times j to the third times k to the third. And then the final term, now 54 is 2 times 27, and 27 is 3 cubed, 3 times 3 times 3. So this is 2 times 3 times 3 times 3, that's 54. And then, j squared, so times j times j. And then k to the fourth, right, times k times k times k times k. Or, 2 to the first times 3 to the third times j squared times k to the fourth. All right. Now, if you're looking here, if you actually wrote out each individual factor like I did here, right, the greatest common factor is just made up of those factors that all the terms share. So they all have a factor of 2. Right, each of them has a factor of 2, so 2 is going to be in the greatest common factor, so 2 times. They don't all share another 2, and then they all share a 3. There's a factor of 3, a factor of 3, and a factor of 3. So there's a factor of 3 in the greatest common factor. They all share another factor of 3 as well, right? There's a 3 here, and here, and here, right? So they share 2 factors of 3. 2 times 3 times 3 in the greatest common factor. And that's it for the numbers, and then they all share a factor of j. Right, so there's times j in the greatest common factor. They share another factor of j as well. There's another factor of j that they all share. So another factor of j in the greatest common factor. And that would be it for the j's. Then they share a factor of k. Right, so there's a factor of k in the greatest common factor. They also share another factor of k, right? They all have at least 2 factors of k. All right, and then putting this all together, 2 times 3 times 3 is 18. And then j times j can be written as j squared. K times k can be written as k squared. So there's the greatest common factor, right, for these 3 terms, 18 j squared k squared. Right, or, again, you could have done it this way. This is probably a little faster. If you wrote out their factorizations as, with their powers, with exponents, you could have found the greatest common factor this way. Right, you notice, every single one of these terms has some power of 2. So the greatest common factor is going to have a power of 2. And the power on that 2 is the smallest one. Right, it's the smallest power of 2, which is 2, 1, or 1. So 2 to the first. Right, times. And then every single term has 3 to a power. So the greatest common factor is going to have 3 to some power. And again, it's going to be the smallest power on 3, which 2, 2, 3, 2. 3 squared. Every single one of these terms has j to a power in its factorization. So the greatest common factor is going to have j to a power. Right, and again, it's going to be j to the smallest power of j. 4, 3, 2, that's 2. So squared. And finally, every single factorization of the terms has a k to a power. So in the factorization of the GCF, there's going to be k to a power. And once again, it's going to be the smallest power of k. That's 2, 3, or 4, so that's 2. Right? And there we go. And then we simplify this. 2 to the first is 2, 3 squared is 9, 2 times 9 is 18, and then you got j squared, k squared. And it's exactly the same thing. Right? I found it in the same thing in 2 different ways. Right? I'd call this the long way, where I list off every individual factor and then box in all the common factors of all the terms. I'd call this the shorter way, where I write everything in terms of powers, write everything with exponents, and then look for what is a common base to all 3 terms, and then what's the smallest power on that common base. Alright, and then finally, we do the factoring. Right, so this original expression is equal to the following product, right? The following multiplicative expression. Right? The greatest common factor comes outside. Right? I pull that out. 18 j squared k squared is its own factor times a quantity, and in this quantity, again, I'm just putting the factors of each term that are left over after I remove the greatest common factor. Alright, so if I remove the greatest common factor, and again, it's nice when I see it this way. You could also do it here too, just remove factors. But what's left over in the first term would be 2j and j, or 2j squared. Right. Then minus, right, the next term, what's left over is jk, j times k. And then plus, and then what's left over, the third term, is 3k squared. Right, and that's it. We have factored that polynomial, by pulling out the greatest common factor. And that's what they're looking for. And again, please don't forget to check your work. Multiply these, redistribute the 18j squared k squared, and see that you get 36j to the 4th k squared minus 18j cubed k cubed plus 54j squared k to the 4th. And you should. If you do, that means you did the factorization correctly. And if you get a totally different expression, either you're multiplying wrong or you just did it wrong and you need to take a look at it again. But you should always be double checking your work. Alright, and that's it. I hope watching me go through these 4 examples here help you in some way when you're asked to factor out the greatest common factor of a polynomial on your own. And thank you very much for watching.